We're going to continue simplifying rational expressions. We're going to mix in variables now. So let's again begin by applying something we already know how to do to a new scenario. So zooming in on this square root one here, the square root of 24, and then I've got some variables. So I'm thinking the biggest perfect square that I know that goes into that would be 4, and 24 is 4 times 6. So I'll just recopy this part. There's a couple ways you can think through the variables. I'm going to model what I think is the quickest way. If you're struggling, I can show you some more scenarios in class. So square root of 4 is 2. Square root of 6 is irrational. That stays beneath the radical sign. Now let's look at x to the 6th power. So I think of this as, if this were in rational exponent form, exponent over index. The index is 2, so we're really doing x to the 6 divided by 2. That's x to the 3rd on the outside. Okay, then y to the 4th, well, the square root of y to the 4th would be y to the 4 halves, or y squared. And z to the 3 halves, okay, so I think how many times does 2 go into 3? It goes in 1 time, so z to the 1st stays out, and the remainder, what's left over, stays inside. So there's my final answer. Now, I'm afraid maybe I lost you on z to the 3rd, so just think another way of thinking z to the 3rd here, when I take the square root of that, would be z squared times z, right? That's z to the 3rd. This one I know comes out as z, and what's left over, the irrational one, would stay inside. So here's my final simplified expression. All right, let me zoom out here, and let's see if we can start applying this to a new scenario. So let's start here with this 5th root of this expression. So I'm going to look at my coefficient, 5th root of 4. Well, that makes my life easier because 4 is not going to break down. There's no perfect 5th powers that go into 4, so that stays inside. Now a to the 8th, I think exponent divided by index. So a to the 8/5. So that means 5 goes into 8 1 time. So an a to the 1st comes out, and I would have 3 a's left over. Okay, again, another way of thinking that through is on the inside, a to the 5th times a to the 3rd. This one I know comes out as just a. B to the 14th, well, exponent divided by index. So 14, b to the 14/5, 5 goes into 14 evenly 2 times. So b squared is out, and I would have a remainder 4 left over. So b to the 4th inside. C to the 5th, well, that's going to be a perfect 5th power, so it comes out as just c. So there's my simplified expression. Right? Not so bad, right? So much like what we were just doing with square roots. Okay, perfect 6th power. So they have the same index. They're both 6th power here. So I'm going to begin by kind of combining my radicals into just one. And 54 times 4 is 216. Go on to the r's. R to the 4th times r to the 3rd is r to the 7th. The s's would be s to the 26th. And then I have a t squared. Okay, so first of all, oops, I just realized I dropped my index here. That's the 6th root. So I want to see if there is a perfect 6th power. So off on the side, I'm just going to see what 2 to the 6th is. 2 to the 6th is 64. 3 to the 6th is 243, so that's too big. So I check and see, is 216 divisible by 64? And I get a decimal, so that tells me I can't simplify the coefficient. So I'm going to leave the 216 beneath the radical, and I'm going to focus on the exponents now. So r to the 7th, when I'm taking the 6th root of this, so exponent divided by index, 1r, r to the 1st comes out, and I'm going to have 1r remaining inside. S to the 26th, well, that's the same as exponent over index, so 6 goes into 26 4 times, so s to the 4th comes out, and I would have 2 s's remaining, so s squared on the inside, and t to the 2/6, let's see, well, that is not going to reduce here, so I'm going to just leave a t squared on the inside. Now, once in a while I have somebody say to me, well, wouldn't that become t to the 1/3? Well, technically that's true, But I would have to then make a second radical, and that almost kind of makes this more complicated, so I'm just leaving it in this form, in the sixth root form. So let's look at how this applies to addition and subtraction. So in order to add and subtract, in a sense, you have to have like terms. So back in Algebra 1, or even pre-algebra, when you did 4x plus 7x, that's 11x. You would combine your coefficients and keep your variable. Similarly, we handled square roots where we would, as long as they were both square roots, we combine our coefficients, 3, and we keep the radical part. So this is 3 root 3. Okay. How does that appear? How is that similar when we have rational exponents? So the variable part would need to be identical, and it is. So this would give me combine my coefficients, -6, and then keep the variable y, x to the 1/8. So let's look at this now with higher indices. So again, they're both to the 5th power in number 7. So I'm going to do -3 minus 2 would be -5 times the 5th root of 4. Now I should think about the 5th root of 4. Can I break that down? No, I can't take the 5th root of 4. Okay, in number 8, cube root of 54 minus the cube root of 2. At first glance, you probably say, well, they're not the same radicals, so I can't, or they don't have the same radicands, so I can't simplify them. But perhaps we can simplify 54. So we're looking for perfect cubes. So I think through 2 cubed is 8. That doesn't go into 54. 3 cubed is 27. And I think that's going to work for me. So the cube root of 54 could be 27 times 2. I'll just recopy this minus the cube root of 2. So cube root of 27, I know, would become 3 times the cube root of 2. Just recopy, minus the cube root of 2. So this coefficient in front of here would be 1. So really I'm doing 3 minus 1 is 2 times the cube root of 2. Again, these numeric ones are good ones just to type the original into the calculator and the final answer and just compare those decimals and make sure that they are the same. It will at least help you catch any silly mistakes you make.